Hello, we are Inyang team. Our members are Li Tingliu, Shen Shendu, Zhongwen Cai, Shuoping Yang, and we are honored to have the opportunity to participate in this presentation to introduce our technical solution. It mainly includes four parts: background, methodology, experiment, and conclusion. Firstly, is the background. Generally, there are great differences between the training set and the actual test setting. As shown in the training set, the training data is generally clear. However, as shown in the real-world data, sometimes data contains more noise due to corruptions, camera-related perturbations, comprehension. Therefore, the challenge is to develop solutions to improve the robustness of the model and narrow gap between the training set and actual test setting. The DOS 2022 provides three datasets for model accuracy validation: HMDB 51P, UCF 101P, and Kinetics 400P, which are all corrupted and perturbed. Then, we will present our approach. This is the overall pipeline. Raw frames are first extracted from provided raw videos. These frames then perform data augmentation between spatially and temporally. The processed frames are then sampled using a constant sampling technique and passed to the R2 plus 1D BERT network and swing transformer network. Finally, the outputs of the two networks are assembled, which produce the final classification. We selected an appreciate architecture for the video domain called R2 plus 1D BERT. This network is based on the R2 plus 1D model, and the TGAP layer is then replaced by BERT to better utilize temporal information. Also, we set the initial point as the pre-trained parameters trained on Kinetics 400 datasets. By observing the dataset, we believe that adding different kinds of noise to the training data properly drop out some pixels of the sample, occurring, scaling, and flipping the sample data can greatly improve the robustness of the model. The nice spatial data augmentation visualizations we used are shown below. Like the above method, we also use data augmentation in the temporal dimension. In order to make the model learn the temporal dimension features more effectively, our data augmentation on temporal dimension includes randomly filling frames, playing in reverse order, video acceleration, and video slowdown, etc. The processed videos can be seen in the following clips. Then we introduce our experiment. We conducted ablation experiments on the network structure. The first group used R2 plus 1D TGAP network. The second group used the efficient net BERT network, and the third group used the R2 plus 1D BERT. The experimental results showed that R2 plus 1D BERT had the best performance on HMDB 51P dataset. We choose R2 plus 1D BERT as the experimental model, and the data augmentation methods in spatial dimensions are used on the sampled video frames. We divide the data augmentation of 9 spatial dimensions into 3 groups and select one group each time for the experiment. Finally, we conduct the data augmentation of 9 spatial dimensions together. Experiments show that the data augmentation strategy improves the accuracy by about 9.58% on HMDB 51 and about 7.34% on UCF 101. We have also done some experiments related to data augmentation in the temporal dimension. We divided 4 augmentations in the temporal dimension into 3 groups, and each time we selected one group for the experiment. Finally, we combined the 3 groups and performed the experiment. Experiment shows that the strategy can improve the accuracy of HMDB 51 by about 4.31%. Finally is the conclusion part. Through the methods and strategies introduced above, our accuracy on HMDB 51P, UCF 101P, and kinetics 400P datasets and reached 92.54%, 92.56%, and 70.55% respectively, and we won the second place. Thank you.